Yes, good morning students. In the previous video lectures, we discussed theory and numerical part of current, electricity and magnetic effect of electric current. Now this session we are going to start the theory part of the another chapter in CBSE, chapter 5, magnetism and matter. So now you please see that is chapter 5 is magnetism and magnetic material. I can shortly write that has to be matter. Okay, so this is the chapter name. In this, what we are going to discuss means the first one what we are going to discuss is properties of magnetic field lines. You know that in electrostatics there is a more correlation between electrostatics and the magnetostatics. Okay, so if you are good in electrostatics, then you can easily understand this topic by just giving a comparison. Now the first topic what we are going to discuss is a magnetic property of magnetic field line property. So magnetic field lines property, magnetic field lines properties. So what is the property we are going to discuss? Very similar to your electrostatics. The first property is, let us consider there is a bar magnet which contains two poles, north and south. So the first point what it says that is the magnetic field lines are coming out from the north pole and is going into the south pole. In outside of the magnet, the field lines are coming from north to south. But inside the magnet, what will happen means the field line is going from south to north. So therefore, inside the bar magnet, the field line is going from south to north. So what is the main difference between that electric field lines and magnetic field lines means there it will be a open continuous curve, but here this one will be a closed continuous curve. So that is the first property. And second one what we are going to discuss is the next one is, as we discussed there, just to see that they never intersect with each other, and the third property what we can say that is they never intersect, the second one. And third one is, you just see that the strength of the magnetic field, or magnitude of the magnetic field is directly proportional to closeness of the magnetic field lines, is directly proportional to what, children? Closeness of the magnetic field lines. For example, you just consider this is the magnetic field, a non-uniform magnetic field. So just consider the two regions which have the imaginary same cross-sectional area. Here you just see that we can say there will be more number of field lines passing through this area. Therefore, here we can say that the magnetic field value is more when compared to here where the less number of field lines are going. So here more magnetic field, here magnetic field is less in value because the number of field lines are very less. So that is the another property. And the fourth one is as we said here, you just see that for a bar magnet, the field lines are very closer, very near the poles of the magnet, which shows that the magnetic field is very strong near the poles. So the poles of the magnetic fields are very strong or more magnetic field when compared to its sidewise. Okay, yes. These are the important property what we must consider. As we said there, it's very similar to, if you want to get the direction of the magnetic field, just draw the tangent. So to get the direction, so if you want to get the direction, you just draw the tangent at the point. So the tangent drawn will give the direction of the magnetic field lines. So say for example, this is the bar magnet, say N and S. This is the field lines pattern S. Now please see that. So it is going out like this. So these are the magnetic field lines which are represented outside of the magnet. At any point, say for example P, if you want to get the direction, you just draw the tangent line, you just draw the tangential line which will give the direction of magnetic field at this particular point P. So these are the very important properties is what we must know before going to the lesson. So the next one what we are going to discuss is another important one is a little bit derivation part. Is, as we discussed in the earlier, there we said that in the previous chapter we said that the value of or whenever the current carrying coil or loop is will behaves as a magnet, bar magnet or magnetic dipoles. That there we proved for is a circular coil, but the same idea will be used here also. The second topic what we are going to is solenoid is equivalent to bar magnet. Solenoid is equivalent to what, children? Bar magnet. Generally bar magnet we can say that magnetic dipoles, because it has the two poles north and south. So therefore let us consider is a solenoid of is length 2L. A solenoid of length what, children? Is 2L. So this is 2L will be the length of the solenoid. I am considering the S coordinate system. Say this is for example x and y. So this is point O, and the value of x at this end is say x equal to plus L, and here that is x equal to minus L, negative x-axis direction. Now let us consider is R be the radius of the is that solenoid. R be the radius of the solenoid. Now you please see that you are considering a point P where we have to measure its axial magnetic field, because in solenoid we know that the magnetic fields are passing through the axis of the solenoid. So therefore this distance is taken as to be R. This distance is taken as to be what, children? R. Now what I am going to do is, you just consider a circular element. You just consider a circular element is okay. You just consider a circular element. Yes. So this is back side of the S diagram. So you can put that is a dotted line. That is our wish. So just consider this is the length element. Yes. Whose thickness is taken as to be dx. Yes. Whose thickness is taken as to be what, children? Dx. Okay. Which is at the distance x from the origin. Now this will act as a circular ring. The shaded portion will act as a circular ring. We know that for a circle, we know that the formula for circle at any point P, say this is x, there we taken x, here we are taken as some distance. So where x is the distance between center of the circular loop and the measuring point, then the magnetic field is given by as B is equal to mu naught Ni R square divided by as 2 into x square plus R square whole power 3 by 2. So this is the general expression what we discussed in the previous chapter. So this is x square. So now please see that this is the ring, the portion which is having the thickness. So for your understanding purpose, I can draw that as that ring circular element. Yes, circular element of thickness ds. So from this center, the point P is at a distance of, this is the circular portion, the element what we consider, and this is the distance. Therefore the distance from this diagram, this will be R and this is x, then we can say that this distance has to be R minus x. Therefore I can say that this distance has to be R minus x. So what this formula x represents, distance from the center of the circular coil and the measuring point. So this is the circular element of thickness dx. So from this circular element, the distance of the measuring point is R minus x. Therefore I can write this formula dB, the magnetic field due to this small circular element. Okay. So dB is nothing but mu naught dn, where dn is the number of turns in this small thickness dl. In solenoid we discussed that n is equal to total number of turns divided by total length of the solenoid. So here that will be n into 2l. So that is equal to dn by dx. Since there will be a uniform distribution throughout the length, the number of windings will be uniform with respect to length. Therefore I can write in elemental point of view. So therefore dn is instead of n, I can write dn I into r square divided by what, children? 2 into this measuring distance is what? R minus x that whole square. So R minus x that whole square plus capital R square whole power 3 by 2. So here we are going to take some assumption that Yes, so the two assumption we are taking. For example, since we are considering it will be a very infinite long solenoid. So for that reason we can say that R is very greater than X, as well as R is very greater than R, where capital R is radius of the solenoid. So by this assumption, the denominator terms can be modified. Yes, because this R square X is negligible because of this condition. When compared to R square, this will be negligible because of this condition. So in denominator we can get that has to be dB equal to. So what children? dB is equal to. So dB is equal to, we can say that mu naught dn is mu naught dn I R square. So this is dn I R square divided by what, students? That yes, you just see that yes, X is negligible, R is negligible, then R square 3 by 2 will be there, therefore we can get R cube. Therefore I can write this has to be as a 2 R cube, students. So from this we can get that dn is equal to n into dx, dn, capital Dn, yes, dn is equal to n into what, children? Yes, dx, therefore I can substitute here, therefore I can say that this has to be mu naught, that is small n, so small n dx I R square divided by 2 small r cube. Yes, so now please see that this is the dB value, the small magnetic field produced by the circular element what we consider. So therefore the total magnetic field is nothing but the integration of the whole system. Therefore I can write that mu naught I R square divided by 2 r cube integral dx. Here the x value, we can consider the element, either right side of the origin or left side of the origin here also. Therefore I can take that the value of x varying from minus L to x equal to plus L, that is upper limit and the lower limit. So we know that the integral dx is x, and if you are substituting the limits, then we can get this integration value has to be as a 2L, where 2L is total length of the solenoid. So therefore I can write the expression has to be B is equal to mu naught I R square into as a 2L, as a small n will be there, so n small n into 2L divided by 2R cube. Now what I am going to do is n into 2L, n into 2L, just to see that n into 2L is nothing but total number of turns capital N. Therefore I can say that, or I can write that mu naught capital N is what is that, children? This becomes to be capital N. Then remaining is what? Ni into R square, capital R square divided by 2 into small r cube. So what I am going to discuss in the, what we are going to do in this, Ni means total current. Ni means what, children? Total current. What I am going to do is multiply by 2 pi divided by 2 pi. Multiply by 2 pi divided by 2 pi. Yes, then what I will get is B is equal to mu naught, the total current Ni, pi into R square. Yes, pi into R square, the remaining term is 2, is whole divided by 4 pi into R cube. This is nothing but total current and the area of the circular part. We know that a current into area is nothing but magnetic dipole moment M vector, as we discussed in the previous chapter. So therefore this term is nothing but magnetic moment M. Magnetic moment what, children? M. Therefore I can say that B is equal to mu naught by 4 pi and 2m is there. So 2m divided by R cube, where m is the total current, n into I into area, pi R square, pi into capital R square. So this is the magnetic moment. Yes, if you consider a bar, this is for a solenoid. This is for what, children? Solenoid. For a bar magnet, if you are measuring the axial field, we can say this is N and S. The length of the bar magnet is taken as to be 2L. Yes, 2L, and from this center O, you can consider some arbitrary point on the axis. Then what is the net field at the point P because of this bar magnet is, that will be also given as to be B axial is equal to mu naught by 4 pi 2m divided by what, children? R cube, where R is the distance from the center of the bar magnet. So by comparing this result with the solenoid as magnetic field, we can say that the current carrying solenoid will behave like a bar magnet, because in lower standard we studied that whenever a bar magnet is suspended from its geometric center, it aligned in the direction of north south, geographic north south. So similarly, whenever a current carrying solenoid is placed and freely suspended in vertical direction, when the current is passing through it, since it will behave like a bar magnet, the solenoid also will turn and aligned in the direction of geographic north south direction, students. So this is very important one derivation. It may be asked in 3 mark or 5 mark category question, but in MCQ point of view, just keep the result in mind. Yes, please note down the theory, students. Topic what we are going to discuss is the third topic is what we are going to discuss is time period of a bar magnet or magnetic dipole when it is suspended in the external magnetic field. So time period expression is expression T. Just to see that, children, most of the cases are very similar to your electrostatics. So let us consider this will be the uniform external magnetic field B vector, uniform external magnetic field B vector. Yes, in this you just assume that a bar magnet of length 2L is placed N and S. Then, as we discussed, the north pole of the bar magnet experience the force along the magnetic field, and south pole of the bar magnet will experience the force in opposite direction. Okay, so this is the force acting on the magnetic dipole. Yes, so let this has to be theta and the length has to be 2L. So due to this, what will happen? There will be a deflecting torque. Therefore, the deflecting torque tau is nothing but, in electrostatics we said that Pe sin theta. Here also, instead of P, here magnetic is moment. Instead of E, here magnetic field. That comparison table we are going to discuss, but you just see that this will be MB sin theta. MB is a magnetic dipole moment, a magnetic field, and sin theta. Yes. For small angles, we can approximate that sin theta has to be approximately theta. Therefore, I can say that tau is equal to MB into theta. For small angles, if theta is small, we can approximate that sin theta is approximately equal to theta. So therefore, I can say that tau is equal to MB into what, children? Theta. Yes. The restoring torque, I can say this may be the restoring. When the field is switched off, the magnet may come back to its normal position because of the restoration. So therefore, I can use the tau is equal to MB sin theta. Yes. And also in 11th standard we studied the oscillation chapter. A condition for angular SHM. Like F is equal to MA, here tau is equal to I into alpha, where alpha is angular acceleration and I is a moment of inertia of the bar magnet what we used. So I can use the a negative sign here, because that maybe will act as the play the role of restoring torque. Therefore, you just compare these two equations. I can get that I alpha, that is equal to minus MB into what, children? Theta. Yes, or I can say that, or we can say that alpha is equal to minus of MB divided by I into theta. Yes, we know the condition for yes, angular SHM, that means alpha is equal to, yes, angular acceleration alpha is equal to minus omega square theta. This is the condition for angular SHM. Condition for what, children? Angular SHM, that means alpha is equal to minus omega square theta. So just to compare this expression, we can get that, yes. So therefore in the place of omega square, so therefore omega square, that is equal to what, children? Is mb divided by si, where I is moment of inertia. Or we can say that omega is equal to root over mb divided by I, where capital M is magnetic dipole moment, or simply we can call it as magnetic moment. In electrostatics we said P is equal to Q into 2D or 2L. Here also we can say that M into 2L. That comparison table we will discuss, but anyway M is magnetic moment. What is omega? That is 2 pi by T, time period S. So that is equal to root over mb divided by I. From this I can get that T is equal to, yeah, so 2 pi. The reciprocal division is nothing but reciprocal multiplication, therefore I divided by M into B. So this is the required expression, time period expression, where I is moment of inertia of the bar magnet and MB is the magnetic dipole moment, or simply magnetic moment, and B is magnetic field, external magnetic field. And this is the one expression. And the same thing we can say that 1 by T is nothing but frequency, therefore we can say that 2 pi f, that is equal to root over mb divided by what, children? I, or from this f is equal to 1 by 2 pi root over mb divided by I. This will be the frequency of the oscillation. MCQ point of view, these relations are very important. Okay, so please be careful with that. Yes. From this, how to find? If I know the time period value of a magnetic dipole, then how can we find out the value of the magnetic field? Means just you square this equation. So therefore, by squaring this expression, I can get this has to be T square is equal to 4 pi square I divided by MB. So from this I can get that the strength of the or value of the magnetic field is given by as a 4 pi square I divided by M into T square. So this is the another expression. So what we must know. Yes. So this is the information about the oscillation of the magnetic dipole placed in a uniform external magnetic field. The another fourth topic or subtopic what we are going to discuss is the potential energy of the dipole. Potential energy of the magnetic dipole. Potential energy of the magnetic dipole placed in the external uniform magnetic field. You just take the same diagram. So here I can consider that this is the bar magnet, it's a north pole, south pole. It experiences the forces along this direction as mentioned here. So there will be a uniform external magnetic field. Say this as theta and this is 2L here. Yes. So we know that angular acceleration in rotation dynamics, you may study that dW is equal to the work done for recurring a small rotation of the bar magnet, tau into d theta, where tau is nothing but a torque equation as we mentioned here. Since there you used minus sign, here we used minus sign, here you use minus sign because it is considered to be a restoring torque. But here we are just considering about the external work done to rotate the magnet. So therefore torque is given by mb sin theta into what, children? D theta. So what is the total work done to rotate the bar magnet or magnetic dipole from an initial angle theta initial to final angle theta final? So therefore I can say that the total work done, since m is constant for the given bar magnet and b is uniform, so that can be taken out from the integration. We can say that integral is sin theta what, children? Theta. So the integration limit is theta initial to theta final. Yes. We know that integral sin theta is minus cos theta. I can take the minus sign outside and substitute the upper limits and lower limits. Therefore I can say that this external work done is nothing but stored as a potential energy, that is given by minus mb into cos theta final minus cos theta initial. So this is the important equation. Yes. In the case, whenever two angular positions are given, you please use this equation. Some cases they may use only one angular position of the as a dipole, magnetic dipole. So for that reason, what we have to be consider is, let us consider if a theta initial has to be 90 degree, that means initially the dipole is perpendicular to the magnetic field. From that position, it is rotated to some angle theta. It is rotated to what, children? Some angle theta. Then this equation can be rewritten as W is equal to U, that is equal to minus MB cos theta. Yes, this is the another equation. We know that A dot B is nothing but AB cos theta. Similarly, this can be written as U is equal to, or W is equal to minus M vector dot what, children? B vector. This is the vector equation. Yes. In mechanics, we studied that when the potential energy of the system is maximum, that is corresponding to unstable equilibrium. When the potential energy is minimum, that is corresponding to a stable equilibrium. So therefore, I can give the condition for a stable and unstable equilibrium. So this will be the say for example stable, and this is what, children? Unstable equilibrium. Yes, in the case of stable equilibrium, what is the condition means? It's very simple. Theta has to be, stable means U should be minimum. So if there is a negative sign, therefore we can see that theta initially has to be 0 degree. Cos 0 is 1 plus 1. Therefore we can get that. So U minimum, that is equal to minus MB. Yes, this is the condition for a stable equilibrium. And if theta equal to 180 degree, then cos 180 is minus 1, and minus into minus becomes plus. Therefore, U maximum, that is equal to plus what, children? MB. The maximum potential energy corresponds to unstable equilibrium. Okay, students. So this is the condition for stable and unstable equilibrium, and expression for potential energy and its different form. Okay. So these are the important as a concept, or the beginning concept in the magnetostatics. The another topic what we are going to discuss is the another important one is magnetic flux. So what is the magnetic flux? Because we are going to define as Gauss Law for magnetostatics, as we discussed there, electrostatics Gauss Law. So similarly, we have to discuss, or we have to define or state the Gauss Law for magnetostatics. So for that purpose, the another subtopic what I am going to discuss is magnetic flux. What, children? Magnetic is a flux pi B. So there we wrote pi E, here pi B. B means magnetic field. Yes, okay. So now you see that. Let us consider a cross-sectional area. Area of cross section whose direction is given as to be outward normal. This data and all, you know that, because there we discussed how to consider the area vector and things and all. So let us consider this is some external magnetic field it's passing through this given area. Yes, the angle between magnetic field lines and the area vector is taken as to be theta. Then the magnetic flux can be defined as pi is equal to surface integral. Yes, all the things I hope that you know what these things in electrostatics. So surface integral of B dot dA vector, or in vector scalar form we can write that as BdA cos theta. BdA what, children? Cos theta. Yes. So here also, as we discussed there, the outward flux will be negative and the inward flux will be positive. Similarly here also, when the flux is, this will be the outward, inward flux. This is the inward magnetic field line for this closed surface. So here the area vector is outward direction. The angle will be 180 degree. So therefore, here inward flux is negative. So for your note, I can say that the inward flux sign will be what, children? Negative, and outward as a flux sign will be positive, because the angle will be, for a positive side, the maximum flux will be, theta has to be 0. Here the theta has to be 180 degree for inward flux, and this will be outward flux. Okay, as we learned in the electrostatics. So yes, this is the thing. Yes, this is the information about magnetic as a flux, and you just see that what is the unit of this one, because it's a dot product, obviously a scalar quantity, and this will be the unit is Weber, is simply called as a WB. Yes, so the symbol form is what, children? As Weber and WB, that means a scalar. Obviously it is scalar since dot product is there. So now please see that the another important point, subject point of view, is what is that means. You just see that Gauss law is Gauss law for magnetism. Gauss law for what, children? Magnetism. So what Gauss law for magnetism says that is, you just see, yes, the magnetic flux through any closed surface is equal to 0. So but in electrostatics we said that magnetic flux, the total electric flux is equal to 1 by epsilon naught times the net charge enclosed by the Gaussian surface. But here there is a slight modification, because why we are getting this type of result when compared to electrostatics, where there will be a non-zero answer. For example, for pi e, that is equal to surface integral E dot dA, that is equal to what, children? Q enclosed by epsilon naught. This is the electrostatics Gauss law. So why here RHS is not equal to 0, but here it will be 0. The main difference is, as we discussed initially in the property of the field lines, is the electric field lines are continuous open curve, but here it will be a continuous closed curve. That is the main reason why we are getting different results here. Therefore, this is the Gauss law for magnetism. So from this, what we can conclude, what important results we can get, sir, means it shows that there is no single magnetic poles. That means magnetic monopoles does not exist. Magnetic monopoles, what, children? Does not exist. Does not what, children? Exist. So this is the important inference or results we obtained from the magnetic Gauss law for magnetism. Yes. So I hope that you people are attentive in the video lectures, and you can note down the theory part, students. Yes, please kindly note down the theory. So now we will discuss the comparison table, so which is very helpful for you to understand or relate electrostatics and this one. Yes. So just to see that chapter 5. That next one is comparison table. Once you know this comparison table, then most of the information is over. So what I am going to compare here means electrostatics and the magnetostatics. Comparison study for electrostatics and what, children? Magnetostatics. So magnetostatics. Okay, yes. What is this, sir? Here, as we said, the first one, the proportionality constant is 1 by 4 pi epsilon naught. In electrostatics, here the proportionality constant K is equal to mu naught divided by 4 pi. Yes. We know that this is 9 into 10 to the power of 10 to the power of 9. That unit we can write, no problem. Whereas the magnitude wise, this one Here the mu naught value will be 4 pi 10 to the power of minus 7. So therefore this value is 10 to the power of minus 7, the numerical value. Yes, this is the proportionality constant used in electrostatics and magnetostatics. And second one is a Coulomb's law. So F is equal to 1 by 4 pi epsilon naught Q1 Q2 divided by R square, where charges, magnitude of the charges. So here also we can assume that is 1 mu naught by 4 pi, mu naught by what children? 4 pi. As I can consider each magnetic pole will have some strength or pole strength, that is simply called force strength. Therefore I can say that M1 M2 divided by what children? R square, where M1 M2 are pole strength. Don't confuse with masses. The M1 values are generally pole strength, is a pole strength of the magnet or magnetic dipoles. And the third one is for a electric dipole, we defined minus q and we define this as to be 2d, for example. Then the magnetic dipole moment is always from negative charge to positive charge. So similarly here, so P vector is equal to Q into 2d vector. The direction is from negative charge to positive charge. So similar analogy also I can make here. So let us consider there is a bar magnet. So this will be north and this will be south. The north will very similar to positive terminal positive charge, and the south is very similar to negative charge. Then what will happen? Yes, the magnetic moment M vector is going from south pole to north pole of the bar magnet. Then magnetic moment vector M vector for the bar magnet. In current carrying system, there we said net current into area, that is different, but here we are talking about bar magnet or magnetic dipole system. So here M is equal to, yes, this will be, yes, for example 2d or simply 2l. So we can say that M into small m into 2l vector, yes, where M is a pole strength as we said earlier. Therefore the direction is, as we said, minus to positive. Yes, that means from south to north pole of the bar magnet. That is the magnetic moment definition. And the fourth one what we discussed is torque equation. Tau vector equal to P cross E, or in vector form, in scalar form we can write that has to be PE sin theta. Okay, PE sin theta. The role of electric field is very similar to magnetic field here. Therefore the fourth comparison what I can write is tau vector is equal to M cross B, or I can say that tau is equal to MB what children? Sin theta. MB what children? Sin theta. So this is the another comparison. The next fifth parameter or the fifth one what we can say means, you just see that magnetic potential energy, electrostatic potential energy stored in the electric dipole, that will be minus P dot E vector, or we can write that minus PE cos theta. So similarly here also we can say that fifth one we can say that U has to be minus M vector dot B vector, that is equal to what children? Minus MB cos theta, minus MB what children? Cos theta. So this is the another comparison. Yes, the next one, the sixth comparison we can say that the sixth one is the role of electric field is, we can define that has to be F by Q naught or simply Q. Similarly here also we can say that the magnetic field B vector is F divided by M, where M is a pole strength of the bar magnet. Pole strength of the what children? Bar magnet. So similarly I can continue the comparison table here. So again the same is for electrostatics, and this one will be magnetostatics. Yes, for the another is a topic what we can compare here, the seventh point we can say that the axial is electric field, E axial and E equatorial for dipole. So therefore E axial, that is equal to 1 by 4 pi epsilon naught is a 2p divided by is a 2p is r square minus Yes, here there we take the distance has to be d, therefore we can write that d square whole square. The direction is along the a positive p cap. This is for axial electric field. Yes, r square minus d square, that whole square. And E equatorial, yes, that is 1 by 4 pi epsilon naught PR divided by, yes, we can say that that has to be r square plus d square is whole power 3 by 2 and minus p cap will be there. That means the direction of the electric field is opposite to the direction of dipole moment in the case of equatorial point. The same analogy I can take here. That means for a bar magnet we can say that is B axial. So far we discussed. So B axial, that is equal to mu naught by is 4 pi. Is instead of P, what I can write? Instead of P, I can write M vector. Therefore, is 2M is R, 2M R, that the direction is M cap. That means from south to north pole of the bar magnet divided by R square minus L square, because the length is taken as to be 2L in the case of bar magnet. Therefore, I can write that this has to be like this. So B equatorial, that is equal to mu naught by S 4 pi S M S divided by R square plus L square whole power S 3 by 2. Whole power what, children? 3 by 2. Therefore, the direction will be, say for example, minus M cap. That means opposite to the dipole moment vector. And the seventh point, what we discussed is the another one, seventh point. Suppose R is very greater than D, and here also we can say that R is very greater than L, then that the terms can be neglected. Then we can say that E axial, I can just write the scalar form since you are already aware of the directions. Therefore, E axial is nothing but what, children? 2p divided by 4 pi epsilon naught r cube. Yes, that negligence and all, you know that this will be neglected, r power 4, and this gets cancelled out, r cube will come. So similarly, yes, E equatorial, that is equal to p divided by 4 pi epsilon naught r cube. Yes, by comparing this we can say that E axial is 2 times of E equatorial. Therefore, E axial is equal to 2 times of what, children? E equatorial. Yes, the same analogy here also I can say that B axial, that is equal to 2m divided by what, children? 4 pi epsilon naught r cube, and B equatorial will be yes m divided by, sorry, please be careful with the constant, mu naught by 4 pi. Yes, so here also mu naught by yes 4 pi. Yes, this will be yes m by r cube. Yes, yes. So as we compared here, you can say that B axial is equal to what, children? Is 2 times of B equatorial. These are the comparisons. The another point what we are compare is, say this is point number I think 9. Yes, so the ninth point, the time period expression for here, it will be 2 pi root over I divided by yes P into E. Yes, where I is moment of inertia of the system, P is electric dipole moment, and E is electric field. Similarly, here also we can say that, and we just now we derived that the time period value is T is equal to what, children? 2 pi root over yes I moment of inertia of the bar magnet divided by M into B. Yes, so this I am giving, so in NCERT or that any books it is not there. So for your better understanding, as I am giving this as to be a comparison table, then you need not to be very much about the magnetostatics if you are good in electrostatics, because most of the concepts are related to that. The another one is there we said that epsilon permittivity. So epsilon is equal to epsilon naught epsilon r. Similarly, here also we can say that permeability. This is permittivity. Here we can say that permeability. Yes, the ability to permit the magnetic field line through that. We will discuss in magnetic materials. For comparison purpose, I am giving here, that is mu is equal to is mu naught mu r. Yes, this is called a relative permittivity or dielectric constant. Similarly, here also we can say that a relative permeability. Relative what, children? Permeability. Yes, So this is the comparison table for what, children? Yes, electrostatics and the magnetostatics. Yes, this will give the very clear understanding about the content of the chapter. Yes, please note down the theory, students.